So the subject of my talk is the necessary uncertainties that are inherent in our calculations of relic abundances and even relic spectrum, because we don't know the cosmology before BBN. So I'm sure that you have seen many times this plot. It's a very nice plot. The only thing is that when you see it, you should realize that all this section is completely unknown. This is an invention of people making this plot, right? That actually there was a universe that is radiation dominated. This is what is assumed here. And where before BBN, there were successive phase transitions and so on. And then finally, this inflation at maybe a scale 10 to the 19 GeV, 10 to the 16 GeV. All of this is invented because the earliest data we have about the universe still are these relative abundances of the light elements that are formed during BBN. Deuterium, helium-4, lithium-7, a little bit of lithium-6. And afterwards, the universe becomes too cold to be able to form any heavier nuclei, and they are formed in stars and so on. And so this happens when the temperature is about below, it starts in earnest at about 0.1 MeV. So the limits, and they have been computed many, many times, imposed by BBN and all subsequent history of the universe from which we have data, is about 5 MeV. So there should have been a radiation-dominated universe with reaches about 5 MeV. This limit is driven mostly by the fact that during BBN, in order to get the beta equilibrium, the neutrinos, mostly the electron neutrinos, must be in equilibrium or almost completely in equilibrium. And so you have to be a little bit above the temperature at which neutrinos, electron neutrinos, decouple, which is about a few MeVs. And so you get to about 4 or 5 MeVs, depending different calculations. So the Big Bang model, this extremely successful model, reaches a temperature of 5 MeV. What happened before is entirely unknown. Now, if you have read, as I did long ago, and that would reveal my age, but in any case, the 3 minutes, right? The 3 minutes, the first 3 minutes, who didn't read in my age, 3 minutes, first 3 minutes by Steve Weinberg, right? There he mentions actually that it was not entirely known if QCD was actually the theory of the universe, or there was this idea that maybe there was bootstraps and so on, and then there would be an explosion of degrees of freedom, and we couldn't really reach an explosion of degrees of freedom, but not an increasing temperature. That was the issue. Now, QCD won. And then it makes all the degrees of freedom that we can compute if we consider that the temperature increases and increases finite. And so because we could actually compute the history of the universe up to very high energies, we do, and we did, but that doesn't make it true. So for sterile neutrinos in particular, and also for other dark matter particles that are mostly produced during this unknown era in the history of the universe, this is very important because different viable cosmological assumptions imply relic abundances and spectra that are different, can be different. So we have to have that at the back of our minds when we see these predictions. Why is it important? And I will talk mostly about sterile neutrinos that are produced in this DW mechanism, namely through active sterile oscillations in the early universe, non-resonant ones. I'm not assuming a very large lepton number in the universe. Then in the standard cosmology, and I will mention, the standard cosmology is the one that I mentioned a moment ago, the one that assumes And actually, you know all the degrees of freedom because they are mostly the ones in the standard model, and maybe some others that your model particular adds up. And the universe continues being radiation dominated forever and ever until a very large temperature. So, the rate is very peaked. It peaks at the maximum temperature, which is this, 130 MeVs, the mass over kV to the 1/3. So if you say that actually this happens in a period that is unknown to us, if this temperature is larger than 5 MeV, that means that for masses larger than very small mass, neutrino masses, then these neutrinos would be produced in this unknown era in the universe. So if you make different assumptions about this era, then you get, of course, different predictions for the production. And in this discussion, I'm going to assume something that is very simple. It's just one single sterile neutrino mixed with an active neutrino, just two of them. But you can see that for other things, the effects will be more or less the same. And so if you see the Boltzmann equation for the production, this is F sub s is the phase space density function for sterile neutrinos, given as function of the Dirac-Fermi distribution for active neutrinos, assume that they are in equilibrium. Then you see actually that there is this rate. This is the conversion rate. And there is the conversion rate divided by h times t. H is the expansion rate of the universe. So you can see that a larger h will suppress the production. A smaller h, smaller than in the standard assumption, would enhance the production. This is for this type of production, which is what we now call, or more recently called, a freezing. The freezing mechanism was very well known even before the name was given to freezing. But this is the build-up, right? The build-up, and at some point there is no more build-up because the process for which you build up runs out of steam, and then you are left with the production that you have. If you would have, like for a WIMP, because I studied WIMPs with the same idea, what happens with WIMPs that freeze out, then the effect is opposite. A larger H, a larger expansion rate leads to a larger density, remaining density. And this is because the rate of production, which is decreasing faster with decreasing temperature, meets H at earlier, at higher temperatures when the density is higher. So the effect for sterile neutrinos, or for all freezing, is the opposite when changing H than you will have for freeze out. And then what I would like to say is that here, for small mixing angles, the plots that I'm going to show have very small mixing angles. So you see that actually this production is proportional to sine squared to theta. At some point, I'm going to use this. Okay, what are the usual assumptions that I call standard? Standard may be misleading, because sometimes we use a standard when we have, a standard because it is the best, because it is the most accurate, because it is, no, in this case it's a standard because it is the most frequent, but not necessarily because it is correct. So it may be a little bit misleading, this name that we adopted long ago. It is a standard because it is the usual, not because we have any indication that is more true than any other of the models that I will present. So these usual assumptions are that the reheating temperature, I'm calling reheating temperature, thinking of an episode of inflation. Reheating temperature is the first or earliest temperature of the radiation-dominated period in the universe in which BBN happens. This is the highest temperature of the radiation-dominated epoch. That this is very high. It's much higher than relevant for all the processes that you are considering. Then the universe is radiation-dominated up to the reheating. The particle content is given by the standard model and maybe some other particles that you assume. And then the entropy of matter and radiation is conserved during and after the production of sterile neutrinos or the particles that you want. These are the usual assumptions. Now, I will talk about some other viable pre-BBN cosmological models, two types of them. Some in which only the value of the Hubble expansion parameter is modified, either usually making it larger, but sometimes making it smaller. And the other is low reheating temperature models, in which you assume essentially, if you want, that you are coming out of inflation at 5 MeV. And I will assume that these models, all these models, become equal to merge into the standard cosmology that we know it works at 5 MeV. Now, the simpler example would be a scalar field oscillating around this true minimum while decaying that dominates the energy density of the universe before it decays. The entropy in matter and radiation then is produced during this epoch. That means that not only the value of H, but also the dependence on the temperature on the scale factor is different. But the universe becomes radiation dominated with the temperature T reheating only after the field phi decays. And before then, the radiation bath is very small component. And so what we have seen is that it is a very good approximation to neglect the production, any production of sterile neutrinos that would happen before the universe becomes radiation dominated. And in this way, we can compute it, we can make the computation analytically. So here it is, this is a low reheating temperature. Let me talk about this before. So for T smaller than T reheating, and we are going to assume that this T reheating is 5 MeV, radiation dominates, and then you have the standard cosmology. For T larger, there is an oscillating phi field, and this is well known that an oscillating phi field can behave as a matter domination. In any case, because the radiation bath is a very small component of the total density, before the universe becomes radiation dominated, the production of sterile neutrinos is negligible, and we are not going to include it. Now, this is work. I met somebody here who is a student of Silvia Pascoli, actually. This is work that we did with Silvia Pascoli when Sergio Palomares Ruiz and Silvia Pascoli were postdocs at UCLA. And this was the time of the LS&D neutrino. And you know, how many times you have heard the LS&D neutrino is forbidden by cosmology because it would. And I was always saying, hey, this is not forbidden by cosmology. This is a very strong statement. Because, you know, we wouldn't know cosmology before, blah, blah, blah. It went nowhere. Again, forbidden by cosmology. So we decided to try a model that actually would prove, at least you have a paper, you know. Having a paper is almost like making it true. In any case, so we tried this model with a low reheating temperature. As I said, making the approximation that most of it, which was afterwards confirmed numerically by another postdoc, Carlos Llaguna, a few years later, you can compute actually the number analytically. And here you have what we predict. You see that you have the right dark matter density for a neutrino of mass keV when the sine square is 10 to the minus 3, instead of in the standard cosmology would be 10 to the minus 7. And this is because it is suppressed by the temperature. So essentially, you need the heating temperature to be smaller than T max, the maximum of production. And then the production is very inefficient. And so it is suppressed. The other way of suppressing the production, it would be to change H. In this case, you don't change the entropy, so actually T is 1 over the scale factor of the universe. There is no entropy production. There are many different types of these models, and there are many more others. I will talk about scalar tensor models and kination models. These are all models that I didn't invent. They were just made in the literature, and we chose them as sort of extreme examples, the extreme that we found in order to show this. And in some scalar tensor models, H may be decreased, which is not easy to achieve. So here it is, kination, for example. Kination is a period in which the kinetic energy of the scalar field, the quintessence, dominates, right? So there is a peculiar dependence of H with T. So it goes as T cube instead of T square. But actually it merges, depending when it merges with the standard model, depending on a parameter that you define really arbitrarily. And so we assume that it merges with the standard cosmology at 5 MeV. The other one are these two models that we call ST1 and ST2, scalar tensor 1, scalar tensor 2. In a scalar tensor 1, and they have a scalar field coupled only through the metric to the matter fields. The expansion of the universe drives the scalar field to a state where the theory is indistinguishable. And you see that at large temperatures, larger than the transition temperature, H is this function A times H, and this is A. You see that it drops to 1 very steeply at a particular temperature, which is the temperature 5 MeV. Here there is another one, ST2. This is more complicated because in order to make H smaller, it's easier to make H larger by increasing the contributions to the energy density, putting degrees of freedom. It's difficult to make it smaller. So you have to hide some of these degrees of freedom into a hidden sector. And this is a little bit more complicated, but still, it has a transition, a fast transition. This is the one that we have sort of simplified the most in order to make it, so this is the ratio, right? It's the square of the ratio of the scalar tensor in this model over H in general relativity, the standard one. This is the square. And you see that actually can be smaller than 1. This is the point. So this is the type of models for H that we have. This is what I have said. This is ST1 with a transition, ST2 with a transition at 5 MeV, the standard kination that goes, and this is low reheating temperatures. In any case, we neglect the production during this epoch, and we take only the production after the universe becomes radiation dominated. Now, this is a busy plot, but maybe I will mention a few things, but it doesn't matter. These are all, I mean, I can go through each of them if you want, but this is all rejected by different limits here. And here you have, this is in the standard cosmology. So here you have, for example, Ptolemy. This is a ridge of Ptolemy. These are some existing limits by Catherine. And these are 3 different stages of plan stages. This is where they are building now for Hunter. Hunter is an experiment at UCLA. If you haven't heard of it, I prepared a few transparencies copied from my experimental colleagues. So nothing that I can explain too well, but just if you don't know. So now this is where omega is equal to omega dark matter. These are all this green here are X-rays limits, including the present X-rays and diffuse extragalactic background. And this star is where the 3.5 keV line, the neutrino that will explain the 3.5 keV line lies. And here it is. It will be, you see here, it's about 10 to the minus 9 or something, a few 10 to the minus 9 in sine squared to theta. Now, if you see the same in low reheating temperatures, here you see this mini boom region, completely free of cosmological limits. Here you see the reach for Ptolemy. Here it's Tristan, which I forgot to mention. Here is Tristan, is this upgrade of Catherine. It's a different collaboration, actually. It's an upgrade of Catherine. And here is H3 for the ultimate phase where Hunter wants to get. So you see that actually this is freed from cosmological and astrophysical limits. And this is because the production is suppressed. Now, these sterile neutrinos do not constitute the dark matter. I mean, here would be the dark matter density, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, and so on. But even here, this is in the reach of Tristan. So, for example, if Tristan or even Hunter, which is the reach of Hunter, would discover a 7 keV neutrino with 10 to the minus 7, which, and of course, this putative 3.5 keV line, well, this would be surprising, happens to be correct, that coming and so on, then you would say, hey, there is something anomalous certainly going on in the cosmology. You wouldn't reject this result because it is forbidden by cosmology. And this is my major point. So here it is. I'm going to go fast here. I put here several so you can see the results. This is a scalar tensor 1. This is the one that cleans up more of everything. You can see this has now cleared up practically all this region that was rejected by astrophysics and cosmology. I would like to mention that also the spectrum changes. You can have, this is the average momentum, where the peak of the momentum is in the momentum distribution. 3.15 is the standard. For the low reheating temperature, they are hotter. This is 411. And for ST1, they are cooler. They are 2.89, although I don't know how you could measure that. But if you could, that would be also a very good indication. Now, the others that I mentioned, kination also helps a bit because the production is somewhat suppressed. ST2 decreases age. So actually it makes this bounce even stronger. So there is a variation in this. And now in the last 5 minutes, I would like to mention a paper here of André. So André can explain to you all this. I didn't attempt to explain. I only used these papers by André and collaborators and by Kelly and collaborators, in which they consider self-interacting active neutrinos. Of course, self-interacting active neutrinos give a contribution to the rate of interactions of active neutrinos and therefore also to the potential. And so they change this. And what they did was to say that by making a search on all possible values of the mediator coupling and mass, André chose a scalar mediator. And in this paper, they consider different models for a vector mediator with the same idea. And here, in all this parameter space, DW production, namely non-resonant production in the early universe, could you could have the sterile neutrinos being the dark matter, the whole amount of the dark matter, account for the whole of the dark matter with a DW production in all this range, which is an enormous range with respect to just DW, which would be just one line here. without considering NSI. Now, what about if you consider now the cosmological uncertainties I mentioned before? So we reproduce the paper of André just by changing by having different cosmologies. And they are here indicated by different colors. So for example, the black would be the range between this and this would be the range where the sterile neutrinos can account for the whole of the dark matter with the standard assumptions. But if you consider now kination, you could go to here. If you consider ST1, you can go to here. If you consider a scalar tensor 2, you can go from there to there. So actually, by changing also, not only the NSI, but also changing the cosmology, you can increase this where they can be the whole of the dark matter for all of this, right? But notice that this is the reach of Tristan, this is the reach of Hunter, the ultimate reach of Hunter. They are forbidden by X-rays, okay? So we did the same thing for two of the models, of the vector models. This is, oh wow. I somehow, this is a paper, it's a recent paper, actually. It didn't, I put it here, yes. This is the paper, actually, but here somehow I covered it. In any case, it's the same paper. So here you have B minus L vector mediator and neutrinophilic vector mediator, the same thing. So if you would have only between the black lines, the two black lines, it would be where the sterile neutrinos can be the whole of the dark matter if you consider the standard assumptions. But if you make others, you open up much more. But in all of them, you see that these neutrinos that could account for the whole of the dark matter would be forbidden in the ranges in which Hunter or Tristan could really measure them. Is there a way in which this could be allowed? So assuming that you have a signal, in any of them, you measure a sterile neutrino. Yes, you could say that neutrinos constitute a fraction of the dark matter. Here we make a search in parameter space for all the places in which the density of sterile neutrinos is equal to the density of dark matter. You can do the same search for 0.1, 0.2, 0.3, 0.4, and actually you don't even need to make a search again, because the calculation is the same, because as I showed you before, the density for these small values of sine squared to theta is proportional to sine squared to theta. So you just move all these lines down by the fraction of the dark matter that you want, and there you have your allowed region. So you move down this line by a factor of 10 to the minus 1, you will have the boundary for the 10 to the minus 1 in omega region, omega dark matter. Now, what happens with these X-rays? These X-rays moves up. This boundary moves up. And so you see the regions, allowed regions move down, the boundaries move up. And so you can allow this region where the experiments could find. And this is why, because the region forbidden by X-ray observations, the boundary of it corresponds to a fixed X-ray flux, of course. And the flux is proportional to the density times the rate. The density is proportional. So this product is independent of sine squared to theta. Thus, if the density decreases by a fraction f, the X-ray upper limit moves upwards towards larger mixing angles by a factor of 1 over f in sine squared. So the regions move down, this rejected region moves up, and it frees up. But you will have to assume that they are subdominant. Essentially, in all these models in which Tristan or Hunter could see sterile neutrinos, we find that they are a subdominant component, but not because of that forbidden by cosmology necessarily. Okay, so this is just my conclusions. I think, okay, so it's discovered sterile neutrinos could be the earliest remnants of the universe from the pre-BBN epoch, yet unknown in the universe. The same thing for dark matter. Many dark matter candidates would be the earliest remnants. So our ignorance of the cosmology at the moment they are produced introduces uncertainties in all the cosmological astrophysical limits that depend on their predicted relic abundance and momental distribution, and should be taken into account when interpreting experimental and observational results. And I'm saying this because, again, recently, Hunter made a proposal to one funding agency, and as part of the rejection came this argument saying, hey, all the neutrinos you could discover are forbidden by cosmological and astrophysical limits. And I think this is a serious mistake, because experiment is experiment. If you find one of these neutrinos, you will see that cosmology somehow, cosmology, non-standard interactions, all sort of battery of things that can become actually to be played in order to see how this fits. So this argument that forbidden by cosmology in order not to fund experiments should not be there. There could be others. You don't like the experiment, it's not well, whatever, but not that one. This is an argument funded in misunderstanding of how much we know cosmology. And then there is this issue. You know, sterile neutrinos could be the earliest, as I mentioned. If a sterile neutrino is ever discovered in laboratory, it could be some information about this pre-BBN cosmology. For example, this putative line, if this would persist, 3.5 keV line, a 7 keV neutrino discovered with a sine squared to theta 10 to the minus 7, you would tend to think, hey, a possibility is a non-standard pre-BBN cosmology. And that according, and many other things probably, but that would give information on that. Okay.
Questions, comments?
Thank you for the interesting talk. So I have at least 3 questions, so one at a time in case other people have. My first question, I can see the low temperature reheating model that sets it at 5 mm, and these are all out of my own ignorance. So, you know, how does that mesh with the hadronic phase transition of QCD that happens at like 150-ish MeV?
We have no idea how this transition would happen in the early universe. We have no idea. All these issues of, if this transition happens in a completely different background, somehow it will happen too. It will happen in a completely different environment. For example, and that depends on the particular example. If this would be the case, it would happen during reheating. I forgot to mention, but maybe this is, maybe we will have an indication of what is the height of the potential during inflation because of measurements of polarization in CMB. It could be, but that would tell you the height during the period of inflation when the particular inhomogeneities that you are studying were produced, which is rather early. But then afterwards, you don't know what happens in the reheating. The reheating could be very fast, and then all this energy would go into radiation very fast, or it could be protracted, very inefficient. All the time that the reheating is churning out, the energy density is reheating, and by the end of the day, when you have a temperature, it has 5 MeV or a few MeV. So even then, we don't know. So it could be that all of this has to be revised. Also, baryon number generation. It could be that baryon number generation, you know, Affleck-Unbind mechanisms work for that. You know, the scalars that have a baryon number, and so on. So everything should be non-standard, but that would make it fascinating, not forbidden. Yeah, that's my idea.
Other questions?
So, I mean, that's great that there are several alternative cosmologies, but how do we tell them apart? If
You can't, because you don't have any remnants. That's what I was saying. You need any remnants. You know, even cosmology is based on experiment and observation. We cannot simply say, oh yeah, we can compute this beautiful thing that I showed at the beginning with all these transitions and so on and so forth, and then say, oh, it is so beautiful, it has to be true. Since when? I mean, since when this works? Absolutely never works, this kind of thinking. So the remnants from this epoch will leave an imprint, but we need remnants from this epoch. Maybe there could be some in gravitational waves that could be measured if they are produced in at this moment. That could give an indication, phase transitions and things like that. Still, we haven't observed them, not in the point. So any remnant from that epoch.
So there might be, you know, just to be a little less pessimistic. I mean, we do anticipate far more stringent constraints on light element abundances and relativistic energy density at decoupling and photon decoupling from the next generation CMB experiments. And let me just say that neutrino decoupling is a long and protracted process occurring over many Hubble times. So you have a number here of 5 MeV, but you know, it's conceivable that things go, if they go on a little longer than a little bit lower temperature, you could have small distortions in the neutrino energy distributions, which arise from out of equilibrium scattering. And that may show up. It's not likely, but it's just possible that that shows up as some kind of moving of deuterium abundance and helium abundance and effective in some characteristic pattern. Just a hope.
Yeah, a little bit more the details of the neutrinos are the earliest relics. We have the active neutrinos, the earliest, and they can show up different things, right? So, but we need some other remnant. Otherwise, we don't know.
Thank you. Other questions? Ah. Go ahead.
Okay. The 7 keV sterile neutrino, presumably, like this would mess with the Z width, and that puts some constraint on the mixing coupling or something. Do I understand that right?
For what?
Well, if there's a sterile neutrino, like the measurement of the Z width, wouldn't it? If it's lower, no. Okay. So what am I misunderstanding?
I didn't understand the Z width. The width of what?
So if you have a sterile neutrino that's very light.
Oh, the Z boson.
Yeah, the number of active neutrinos is still 3. So the sterile neutrino doesn't do anything. If you sum, the Z still decays into all neutrino mass eigenstates. But if you sum all the couplings, they add up to 3 states. So that's not a constraint.
Yeah. So I'm sorry, I didn't understand the Z. I didn't expect, yes.
I didn't understand
this would
my
be,
question.
yeah, exactly.
I have a really boring question.
Boring is good. In any case, you know, I don't want to. Kev is, yeah. So
On the slide 2. Yeah, on the slide 2.
You're fine with that.
Slide 2, you had a number that was 130 MeV.
sorry.
There's on slide 2. There's a number. There was 130 MeV.
You want me to go to?
Sure, it'd probably make my life easier.
130. I don't remember. In which one slide?
Slide 2.
2. 2.
Yeah, the 130 MeV in front of the T map.
Yes, it's about.
I mean, it's strikingly similar to the QCD phase transition. I was just curious where the number comes from. Like, is that obvious?
It comes from, if you want me to answer it.
Yes, please.
It comes from, you get a thermal mass to the neutrinos, and so it suppresses oscillations at early times. When you fold that in, an in medium mass, when you fold that into the interaction rate, it suppresses coupling at early times, and but then eventually disappears. So sterile neutrinos were really the first freeze-in dark matter. Basically, they freeze in but never gets to a gamma over H above 1.
The Frisian, exactly.
And we actually, George and I wrote a paper in 2002 saying that you could actually explore the quark hadron transition if you detected the sterile neutrino in X-rays.
Yes.
Yeah.
No, I was just saying.
No, but yeah. But besides, in the other non-standard cosmologies, we computed this. It's not very different. Still happens, in the hundreds of MEVs, in all the ones in which we follow the evolution that far.
Have you thought of some ideas of baryogenesis at this low reheat temperature? Or have others thought about it?
Baryogenesis, there are so many different ways of generating baryogenesis, and I'm sure that there is one that will work in every single type of cosmological model that we can come up with. There are so many ways of doing it.
Yeah,
so, no, I haven't. None of these models are complete in the sense that without the motivation of studying any of them, they tend to be more complicated and so on. So why study this one and not another one, right? But this motivation could actually be there if there is some indication that any of them or any of these non-standard ones, and I'm sure that then I have an enormous confidence in the ability of theorists to come up with models for everything. So,
well, the standard, the widely discussed ideas like weak scale baryogenesis or leptogenesis, they won't apply here, right? So
yeah, so you will have to do things differently during the reheating, and it's a different background essentially, right. or in different background. In different background, age changes, but your processes are the same. So actually, the speed of the evolution of the universe shortens up. So if in a particular model you would overproduce, then with a shortened time you may produce the right amount and stuff like that. So it will change the parameters of many of your models, but not necessarily invalidates them.
Okay. Other questions, comments? Well, if not, let's thank